Recording in progress. Welcome, everybody. Happy Monday. Today, we're going to tackle the second part of materials, which is transparency, transmission, and refractions. So, don't forget today at 1 p.m., there will be an optional 2-hour discipline campus lab. It's basically SAL and VSD getting together. Those are the two sister classes. It is totally optional. We will have a proctor, Tom Boldman, excellent artist, excellent shading and lighting artist as well. So he will be there proctoring, meaning kind of running the lab. If you show up there, you will be logging into Zoom, just like you would from home if you were doing our Zoom lab, the one we do after campus. We're still going to have the normal lecture, the normal lab afterwards. Nothing with that has changed. However, some students had expressed an interest in trying to, go to campus on a limited basis. So Full Sail decided to offer this and see how it goes. If you decide to go, it's in Full Sail 4B 132 from 1 to 3 p.m. Let me know ahead of time if you plan on doing that. That way I can let Tom know just to make sure to look out for you. Office hours tomorrow. Got a doctor's appointment early, but I will be in by 11. I should be. And I'll be there till 5 o'clock since I'm going to come in an hour later. And then Thursday, I'll be on from 10 to 4 p.m. And then on Thursday, also, Frank will be doing the campus and online virtual Zoom lab, kind of our open lab from 1 to 5 p.m. All right. So today we're going to be doing transmission, refraction, transparency. We're going to be dealing with the index of refraction. If you remember the index of refraction for metal, we had a refractive index and extinction coefficient. All right, so refractive index, the same as index of refraction. This is basically how things look when they are reflective. And for glass, how they look when they're reflective and transparent. Okay, so metal, pure reflectivity. For glass, refractive index, this tells the light ray what to do when the surface is transparent and reflective. So that refractive index does a lot. It tells the light ray how to bend. It tells the light ray how to reflect. So the extinction coefficient is kind of a helper for the refractive index, kind of like a secondary multiplier. So PXR surface and refractions, and it is actually under the glass section. It has its own section. Now, Project 6, the material discussion and the research discussion are both going to be due by tomorrow before midnight. Anybody have any questions so far? Anything we went over last time? Brianna, Moesha, Pete, Seth, Zachary. Okay, Zach is good. Brianna is good. Moesha is good. Pete's good. Seth is good. Excellent. Thank you. Appreciate participation. So in transmission, transmission is actually a fairly simple yet kind of fickle natural phenomenon. The reason I say fickle is because it requires that a light ray pass through a medium like clean air or even super clear, clean glass. And what will happen is, now, as the light ray, as you guys well know, our environment, we're kind of swimming in an atmosphere of gas, air, mostly, good portion oxygen, hydrogen, a little bit of carbon dioxide, a little bit of methane. There's, some trace elements of other breathable things that we breathe all the time. Okay, but it's basically kind of swimming around, right? So we have light rays going through it all the time. And for the most part, on a clear day, they are unobstructed. In Florida or anywhere where there's heat and humidity, right? You have a lot of moisture in the air. So sometimes the light ray will bend as it goes through the air because of all the moisture. And you can usually see that on a real hot day, say out in a parking lot somewhere where you get a lot of heat coming off of the asphalt or concrete. And you can kind of see those wavy patterns, or not patterns, but that kind of wavy looking environment behind it, where you're actually looking through the moisture vapor as it kind of heats up and moves around in the atmosphere. Yeah, so, it's basically all the moisture particles heating up and kind of moving around. Makes for interesting convection if you're flying. The hotter it gets in the day, like you fly over a lake, it's going to be a little cooler. You fly over like ground, it's going to be a little warmer. So you get all this, especially if you're in a light plane or a general aviation plane. You kind of, we affectionately refer to as changing seats in the cockpit. So amusing. Can be a little jarring when you first start doing it, but after a while, you kind of realize, all right, yep, I'm going to go over this area and it's going to be bumpy. Okay, so anyway, what happens when we have this light ray passing through a clear surface, like clear, pure glass, is the light ray has to hit that surface at a perfectly perpendicular angle. Okay, so basically 90 degrees. A perfect 90-degree angle. Perfect. Well, kind of scribbly, but perfect. My word perfect is not perfect, but the intention is. So anyway, you have a light ray going through clean, clear air, hitting a perfectly clear, clean, super high quality glass surface. Light ray goes straight through unobstructed, meaning it does not have its course or, trajectory altered. Now, you get into having a light ray hit at an incident angle. Okay, incident ray, incident angle. Anything other than perfect 90 degrees. And what will happen is the ray will hit the surface. It will bend according to the properties of the surface, whether it happens to be glass or plastic or water or ice. It can pass through, it will bend according to the surface properties and exit and continue on its way. This is refraction, basically. So transmission, light rays pass through, they hit the surface at a perfect perpendicular angle. You don't see any bend in the light. Everything looks good. You have an incident ray, which means we've got a surface. We've got a light ray that is not perfectly 90 degrees. It is anything other than that perfect 90 degrees. So the light ray will hit it. The surface is transparent. It will bend according to what the surface is made out of and continue on its way. Welcome, Edner. All right, so two very simple properties, transmission and refraction. All right, now, you guys have all modeled something very similar to this glass. Right? We have you guys model this as it exists in the real world so that we can have our materials and our light react accurately and physically the same way they would in the real world. Yeah, glasses with NURBS, or you can still make them in polys. You just use a CV curve, change your output from NURBS to polys, you know, put it on your control points. It'll make your poly mesh surface, you know, sort of like your NURB surface, and, you know, off you go. Usually you start somewhere in the center, usually line this up with a grid line, click, put your CV all the way around, lock it in the same position as your starting point, do a revolve, poly output, life is good. So we do that because this area in here, this area right here in the middle, this is our material. Okay, what's outside and what's inside? So what do we have outside of our surface? Anybody? If our glass existed in a real world, what would this outside be? Air. Yep. In CG, yeah, with CG air, we just take it for granted that it's air. What about inside? What's inside this glass besides light? Yep, air. I would say that is accurate. So we have air outside, air inside. Air is fairly neutral. Has an index of refraction of 1.0, which is very neutral. It's almost like nothing is there. So consequently, we have light rays that can pass through it unobstructed. All right, so let's say we have a light source here. Got a big old spotlight here. So our light rays go through this air pretty much unobstructed. All right, so what's going to happen is we're going to have light ray come down. It's going to hit the surface. Now, when it hits the surface, this is where the light ray says, hey, I just hit something. What are you made of? Are you opaque? Are you transparent? If you're opaque, I bounce off. If you're transparent, I go through. But what is your index of refraction? All right, so we have the glass saying, okay, well, the glass saying, I'm glass, my index of refraction is 1.5, yeah, 1.52, somewhere in there. Some, like RenderMan uses 1.5, Arnold uses 1.52, I think V-Ray uses 1.52. The old mental ray that we used to use used 1.52. So glass. So our light ray is going to go, oh, okay, well, I need to bend according to your index of refraction, so I'm going to bend. And then our light ray exits, doesn't find anything there. So our light ray can sort of continue on its journey. Now notice its course is changed. Or maybe it's even a little more dramatic than that. Maybe it goes down a little more like that. All right, so then it hits this inner wall of the glass and it says, hey, what are you? It says, hey, I'm glass. And he says, okay, well, I need to bend according to your index of refraction. So the light ray bends, exits out of the glass, doesn't hit anything at all, and continues on its way. So our light ray has actually had 4 different queries. Once when it hits the glass, once when it exits the glass and encounters nothing, hits the inside back wall of the glass, bends according to the index of refraction of that glass, exits out, doesn't hit any obstructions, doesn't hit anything. It says must be air, and it continues on its direct path. So all of those little points we need to know about. Because if a light ray does that, our camera ray is going to do the same thing. So in order for us to see through this, the camera is going to encounter the same things that the light does. Now we'll see our light shadow based on, the angle of the light to the angle of the camera. The camera in this case is looking through the glass at a 0-degree angle, like straight on, face on. So the total number of refraction rays needed are going to be 4. Why? Because we've got one surface, exit out, that's 2, hit the back wall, that's 3, exit out, that's 4. To see on the other side of this, we need to make sure we have 4. Because if we stop after 3, guess what? We're only going to see into the glass, and then we will stop at the back wall. We wouldn't be able to see the background here. Does that make sense? Any questions? So Pete's good, Seth is good, Brianne is good. Moesha, you good? Edner? Questions? Edner's good. Okay. So Seth is good. All right. Excellent. Now, let's continue on. Suppose that we have water in the glass. So let me just get this. Yeah, I know we don't have black water, but this is just an example. All right, so same thing might be here. In this case, let's go with white. Sloppy, but my hand is sticking to the tablet. All right, so, normally this would go on all the way around here. So let's kind of reconfigure this. So now we've got water inside. Now, did they show you guys how to model water in modeling? Did they show you guys how to model a water surface in an object, let's say, a vessel, in a glass, in a bottle, or anything? So Brianna said, not really. Pete says, don't believe so. Okay, well, when I used to teach modeling, the easiest way really is to select your poly faces inside the glass. You can duplicate faces, scale them in ever so slightly, cap off the top. Now, when you cap off the top, you don't want it to be perfectly flat against the sides, right? What you want to have is the sides here, and you want to have the water kind of pull away a little. Like that, because there's this thing called surface tension, right? So there's going to be a little tiny bit of gap on the edges. Kind of, I guess, similar to kind of like a bevel, but on a pretty small basis. So what happens when we do that is we have another surface for our rays to worry about. Now, let's go back with red again. So we have our light ray coming in, hits the surface. Our surface says, hey, I am opaque. So the ray says, okay, I will bend according to your index of refraction. So it bends. As soon as it exits that surface, it hits the water surface. So that water surface, so it hits the outside of the glass, exits the inside of the glass, immediately hits the surface for the water. And for the water, the water surface says, hey, I'm solid and I am water. My index of refraction is 1.3. Okay, so for water, dang it. Come on, get back there. There we go. So water, index of refraction 1.3, 1.33, something like that. So then our light ray is going to bend according to that surface. So maybe it bends something like this. It immediately exits, hits the inside of the wall, and says, hey, guess what? I am opaque, or I'm transparent. So it bends according to the index of refraction and then out the other side. So now, in reality, our surface has 1, 2, 3, 4, 5, and then 6. So ordinary glass, ordinary empty glass, let's say, has 4 surfaces for a ray to go through. glass with liquid. We'll say water inside because that's a nice, easy one to get. Has 6 surfaces. So light ray hits the outer wall, exits the inner wall, immediately hits the solid water surface, exits the solid water surface, immediately hits the transparent glass surface, goes through the glass, bending according to the index of refraction, exits out on its way. So why do we care about that? Well, we have to keep, yes, Seth, you're absolutely correct, 6. So we have to keep track of this because in our render settings, by default, we only get for free 4 surfaces. That's RenderMan set up to have an ordinary glass container be see-through all the way. Once you start adding in extra surfaces, you are adding in extra time for the rays to go through them. And we have to account for those extra surfaces, which in turn will give us extra render time. So I don't know if anybody's done any test rendering, but going from flat diffuse gray to, a rendered scene with materials that reflect light. Maybe you've got some metal in there. Okay, all of that reflectivity is going to increase our render time. It's going to increase it because, we have to track the rays bouncing a lot more. Plus, we're going to have things like roughness, smooth surfaces, in addition to light and shadows. Remember our shadows in lights, hard light, hard shadow, renders pretty quick. Soft light, soft shadow takes a little time to clean up the noise. You have a surface with a soft reflection. That's a rough surface. So consequently, your light, your highlight for your light is scattered. It's blurry. It's going to take time to clean up. And now we're adding transparency to the mixture. So be prepared for render times to take almost twice as long as they did, depending on your camera angle. And depending on the amount of overlap you have with transparent surfaces. All right, let's do a quick little exercise here. Let's see if I can illustrate this in not too disgusting a way. So let's pretend we've got another container here. Right, we got a glass container here. All right, so we've got a glass in front of another glass. And let's say this glass also has liquid in it too. Now, the areas where they overlap are the areas we're most concerned with. Why is that? Well, here, forget the water, how many surfaces does my ray have to go through up here? Right here by itself. Anybody? Yeah, 4. Very good. How about down here where there's water? Yep, we got 6. 4, we got 6. Same thing over here. So we'll say 4, we got 6. How about where these guys overlap? Right in the middle here. No, we got 4. We got 4. Exactly, Moesha. We got 8. How about down here where the liquid overlaps? Now we've got 12 exactly. Right here. That's 12. Because we've got two glass containers with water in them where they overlap, we're going to have 12. So again, increase in render time. All right, good. You guys seem to have that pretty good. Let's go on. So we're back to the conservation of energy. Remember, diffuse plus reflection plus refraction equals 100% of the energy. Now, with glass, we are basically turning off, well, we're not basically, we are turning off diffuse. So there is 0 diffuse. The nice thing about glass is it has its own control for reflectivity or specularity. Down here, we've got a refraction gain and a reflection gain, and this number controls the refraction and reflection and how they interact and behave. So basically, it will give us an accurate amount of transparency, refraction, and reflectivity, and the right or correct ratio. Glass is more transparent than it is reflective. All right, so we're still trying to maintain that physical accuracy.
Can you actually pull up those lines one more time? I didn't get the screenshot of that. Sorry.
Which one? These?
No, the red lines that were on top of it.
The red lines.
You know how you're
here?
drawing lines? No, in the previous slide, you were on the right slide.
Oh, here.
You had a bunch. Yes.
Yeah, I don't know if let me see if I can redo. No, Zoom's not letting me redo. All right, so basically, we have 0 diffuse. Okay, we don't have to worry about reflectivity because this glass section is self-contained. Glass is physical. This number right here, the refractive index, will tell the refraction and reflection what the correct amount is. So for glass 1.5, 1.52, it's going to bend light according to the index of refraction, and it's also going to reflect light according to that index of refraction. Okay, so refractive index will automatically I guess the best word is distribute. The refraction and reflection energy. All right, does that make sense?
Thank you. Yeah, it makes sense.
Anybody else? So just like metal, we turn off diffuse gain. Diffuse gain, 0. We don't mess with primary specular at all. Gone. Come down here, we tell the refraction gain and the reflection gain, we turn them all the way up. Why do we turn them all the way up? Because we want them to be fully charged so that the refractive index can then distribute the information correctly in the correct proportion and balance. So making glass is actually super easy. Okay, Pixar, they say in their docs, keep the refraction gain, reflection gain at 1. Both of them have to be the same. And the material will distribute the energy physically accurately based on the refractive index. You can use other numbers to get interesting effects, but then that kind of breaks the physical property of the material. Great if you're trying to do stylized stuff. So, as I mentioned in the previous slide, creating glass, you'll find you get the best result when you turn off the diffuse gain. Will interfere, unless you turn it off, it will interfere because you'll be getting some of that, whatever color is in the diffuse, bleeding in. Sort of like what happens with metal if you don't turn off the diffuse gain. You'll always get that kind of milky looking metal because the gray or whatever color you have in the diffuse is going to bleed in. All right, so refraction gain, it's a multiplier, very similar to refractive index extinction coefficient, except this handles refraction, this handles reflectivity. We have color. All glass or all transparent materials get color in the refraction color. Remember, we turned off the diffuse, so there is no diffuse. We are not using primary specular, so there is no specular. It's all about glass. This goes for liquids also, right? Because if you're going to make liquids, they're going to have sort of glass-like properties. They're going to be transparent, unless you're dealing with something like milk. Then you're dealing with subsurface scattering, which is way beyond what we do. We're dealing with simple liquids like water, wine, certain kinds of juices. Again, orange juice would be an example of a really kind of dense, viscous, subsurface scattering type material. But things like apple juice, grape juice, things that are more or less clear, tea, coffee, certain, I guess, carbonated beverages also. Now, just like light, refraction color will saturate very quickly. It will look really cartoony and dark. Unless you've got super dark looking glass in your reference, you're probably not going to have really dark saturated colors. You find that, color is going to be probably a lot less saturated than you think. Now, the roughness in the glass section diffuses or disperses the transparency, thus creating a frosted look. Put a glass in the freezer, wait like 5 minutes or so, pull it out. The glass is colder than the air around side, it's got moisture in it. All that moisture condenses on the outside of the glass. Yeah, kind of looks like a beach glass. Cold beverage, warmed air creates condensation. Now, if you're really going to do condensation, roughness works for the really, really fine water particles. But, if you've got a close-up shot, you probably have to model those little beads of water on the outside, and they would get their own material and their own index of refraction, would be water. But again, if we have a lot, excuse me, a lot of roughness in the glass, we are going to also increase render time, because we are not only creating a rough reflection, but also a rough transparency, meaning diffused, dispersed, visible rays. All right, does that make sense? Any questions so far? Pete's good. Brianna's no questions. Moesha. Seth, Zach, Edner, questions? All right, Edner's good. Seth is good. Zach, any questions? Nope. All right, excellent. All right, so index of refraction. Okay, 1.5 is the default. In fact, that is the default for pretty much every renderer that I can think of. RenderMan, Arnold, V-Ray, they all start off with that same index of refraction. It's glass. Higher values, the rays are going to bend more than lower values. Now, one thing that we have under the advanced section, so I mean, if you're doing ordinary glass, under the advanced section, you leave your index of refraction at 1.5. If you're doing, say, water, right? So you would plug in for water 1.33. If you're doing wine, say, for example, or I don't know, 1.39 something. Little bit different, but it will bend light a little bit differently than water. You know, I think like an ordinary clear drinking bottle, something like 1.4, you know, plastic drinking bottle. If you are doing windows, window panes in particular, okay, you're doing an architectural rendering for a client, right? They're modeling and, you know, they've designed an office, you've modeled it. You are now trying to show what the light looks like when it hits the office on the outside, and inside you're going to be showing, you know, nice shiny metal, polished floor, you know, nice polished wood. You're going to be showing that office like it would be brand new, you know, clean, almost perfect. Here's the thing. When you model windows, you are not going to model little tiny cubes, right? You are going to model planes and put them in their place. So why calculate the thickness of glass if it's not needed? Because when we look outside at a building, we really don't see the refraction that much. You know, we look in, we see the office. We're inside the office, we look out, we don't see refraction until, you know, maybe a door is open, so you're actually not looking through glass. But that's pretty rare. For a rendering, you're going to be using panes or planes, and you turn thin on. And what thin will do is not calculate refraction, but create the correct transparency and reflectivity of glass. So it will save you a ton of time if you've got like 150 windows. For today, the interior scene has actual glass. And we're going to talk about that when we get in to do the demo of the interior. So all other objects will have this unchecked, but window panes, you check on thin. Now, another possibility would be if you're just modeling, say, a sphere, right? And you want it to kind of look like an ornament. If you turn on thin, it will create a hollow looking sphere. Like the outside will look like thin walled glass and inside will be air. As opposed to model a sphere, turn this off, and then that sphere would be a solid chunk of glass. All right, so I actually have a couple quick renders here. So I took a sphere, I have a shadow catcher under it, a dome light, simple dome light. Okay, and all I did was change the index of refraction on the sphere. So here, the default air 1.0 neutral. Unless I had a shadow here, you would never know there was a sphere there. Now, same sphere, index of refraction 1.33. So all my glass settings are the same. You know, I've got my refractive index all the way up, my reflection index all the way up, or sorry, gain, refraction gain, reflection gain all the way up. And by the way, the default color for glass, come on, there we go. Wow, Zoom, you just really torture me. Okay, default color is white. Forgot to mention that. White is clear glass. So all the settings equal, changing index of refraction. Now you notice that my sphere, it refracts light. You can see kind of bend. You can see I have a highlight. You can see I have a transparent shadow. 1.52 bends light a little bit more. Right? A little more reflective. 2.42, a diamond, super hard, super dense material. Okay, refracts light and reflects light a lot more. So all of that happens automatically based on this IOR, or index of refraction number. All right, does that make sense? Any questions so far? All right, just check in, make sure everybody's good. All right, so a couple more things and we'll get into doing some demos. What we're going to do is, after we get through this, got a couple more points to make. We'll demo the exterior, then we'll go inside after break and demo the interior. And I'll show you a couple things. Like, for one, we're going to turn on the geometry for the glass windows, and we're going to apply a couple of glass materials to some surfaces in there. All right, so like I mentioned in the last lecture, in the render settings, right? Anything in the render settings is a global control. All right, so render settings equal global for your entire scene. All right, so under render man tab, under sampling, right, go down to default ray depths. The defaults are 4 and 1. Now, as you increase the amount of diffuse bounces, you're going to see light kind of bouncing around, in indirect areas, probably a little bit more. One second. All right, so max specular depth, like I mentioned back here, we get 4 by default. That'll make this glass look perfectly fine. But as soon as we add another glass in front of it or behind it, or we add liquid to it, then we need to change. And we change it based on the global needs of our scene. All right, so we got some ordinary glass objects, and these objects will also mysteriously be in your scene as well. So here we have kind of an ordinary, hourglass shape bottle. We've got a vase. We've got a rectangle bottle. And we have this thing here called a Klein bottle. And this is what a Klein bottle looks like. If you've never seen one, believe it or not, there are like websites devoted to people who are fans of Klein bottles. So basically, Klein bottles work on a kind of complicated but yet simple principle. All right, so you've got an area at the bottom that's open. This is actually the opening of the bottle itself. So you fill it this way. Water goes, or liquid goes up here. Comes around and lands in here, and it fills the bottle up. So this was, basically a mathematical enigma until modern glass making processes. If anybody's ever seen or done any glass blowing, I mean, a molten piece of glass on the end of a big long tube that you blow and you shape and rotate and turn with a tool. Okay, it's really hard to get the neck of that bottle to go into the body. But there are people who specialize in custom making Klein bottles like that. It's much easier with injection molding. So injection molding, very simple, right? Get your shape, you pour it in there, you inject your medium, could be, resin, could be glass, could be whatever it is, and conforms to the shape. It cools, you open it up, and bang, you're done. But here's the thing. How many surfaces would a ray have to go through with a shape like this? Forget the liquid. Let's just look at this, for example. Well, let me get a better example of a Klein bottle here. All right, so come on, there we go. All right, so Seth said he would think 8, not including the liquid. All right, so let's see. We've got outer wall, right? Goes through, got an inner wall. So 1, you got 2, you're coming in here, you got 3, you got 4, light rays going through, you got 5, you got 6, you got 7, and then you've got 8. So yes, 8. Now, if you have liquid in here, you're going to add another 2 in there, right? Because you got liquid. So the reason I mention this is because we want to set our render settings up for, I hate to say the worst case scenario, but you have to set up your global settings for your entire scene. So here we've got 8. The bottle by itself here, we've got 8, or sorry, we've got 4. The vase is 4, but they're overlapping. We got 8 here. Now, this little tiny hourglass bottle actually has a lip that does this. Kind of got like a mushroom lip on it. So here, you would also have 8 for this. So you always have to look around, because if you forget this and you render it out, you're liable to see like, not a black hole, but your transparency is going to stop. You'll either see gray or white or possibly black. and it's going to drive you crazy. But you have to remember to increase the number of default ray depths in the max specular. It says specular, okay, but this handles both refraction and reflections. Make sense? Questions? Okay, Seth is good. Pete's good. Edner's good. Moesha's good. Zachary's good. Brianna? Questions? Nope. All right. Now, like I said, both scenes were rendered. Okay, older Mac, obviously. Much older, as a matter of fact. And it took me 1 hour and 6 minutes for the long shot. The close-up shot here took me 2 hours and 11 minutes. Same render settings. The only thing that changed was the camera angle. And of course, it has to calculate all of that. So be prepared for your render times to double where there's a lot of overlap. Now here, it's all glass. That's why it took so long. In your scene, you're only going to have, like for the close-up shot of the exterior, you're only going to have a bottle, wine glass, wine in the glass. For the interior, you're going to have a Klein bottle on the table at the close-up. All right. Now, let's go make some glass. And I have a little checklist here for you for making glass. So first thing you have to do is obviously find reference. Just like with metal, you want to assign a new Pixar surface to the geometry. You want to turn off diffuse gain, skip primary specular. You go to the glass section. You turn up the refraction and the reflection gain both to 1. Okay, refraction color based on your reference. White is the default, which is clear. And you adjust your glass roughness based on your reference. Okay, under advanced, if you have a liquid, you're going to have to change the refractive index from 1.5, which is the default for glass, to, if it's water, 1.3, if it's wine, 1.38 or 9. Okay, if you're doing window panes, under advanced, you turn on thin. Don't forget, in any circumstance, you need to adjust the render settings, right? So RenderMan, sampling tab, go down to default ray depths. You're going to adjust the max specular. It's the total number of surfaces array has to go through or bounce off of. So there's your checklist. Let's see if we can do that. All right, so there is your checklist for glass. If you are watching this archive, just pause the recording, take a screenshot, and you've got your checklist for creating glass. All right, so first thing, we're going to be doing the exterior scene. So exterior scene basically is this. And I'm going to go by the close-up because this is where the glass is right here. So we've got wine glass. We've got wine in the glass. We have an empty wine bottle, empty being the key word. You need to find reference of empty bottles. Common mistake, finding a bottle that's full. And a lot of times those full bottles will be super dark. You might not be able to see through it. The objective here is to be able to display or demonstrate that you understand glass and transparency and refraction. Okay, so before we get started on our journey looking for glass reference and all that, let's see exactly what we have in our requirements here under the glass or, oops, wrong project. Let's go back to 6. There we go. Jumping ahead of myself. All right, here is your Lecture 7 milestone. Just back that off a little. There we go. Okay, so interior, exterior. We're going to be doing exterior first. So we've got a wine glass, wine geometry inside the glass, bottle of wine, empty. Assign a pixel surface to each of those. We've got a label on the wine bottle itself. We're going to put that on a display layer and turn off visibility. We will use it in Project 7 if needed, but it's only going to cover up the bottle and we're not going to be able to see the wine bottle itself that well. So the wine glass will be clear, but the wine bottle will need to be colored glass, and the wine in the glass needs to be a colored liquid based on your reference. So whether you do white wine, red wine, pink, blush, rosé, Zinfandel, whatever you want to call it, okay, that's your choice based off your reference. Find reference for everything you're doing. All right, so we kind of got an idea of what the Klein bottle looked like. And now I don't want to spend $73 on a Klein bottle, however lovely it is, in the Acme Klein Bottle Company. Yeah. Right out of, see, I told you, man, there are people that are completely fanatic about Klein bottles. All right, so that's all fine and well. Let's just back away from that craziness for a second. And let's start looking for wine in glass outside. Now, a lot of times you'll find single glasses, great, no problem. Having both of them together, like for this one, that's nice. Now you can figure out, do I want to do white wine? Do I want to do red wine? Now, something like this, that's probably fine in real life, but it still needs to be a little more transparent for our purposes. So something like this would be acceptable. You can see through it. This one, too dark. That wine is purely opaque. Not suitable for our purposes. That will not demonstrate that you understand how to get a deep, rich color that's still transparent. So this one, not too bad it is a little too dark. Too dark, too dark. You know, you're really looking for this one where it's, you know, kind of got some light back there. You can see through it. You can see that it has a lot of clarity. That would be totally acceptable. Something like this, not acceptable. Why? Well, it's got one of the matrix white backgrounds. So Zinfandel, blush, rosé, whatever you want to call it. So here, looks like our white wine is chilled. Our red wine is not, but you can't see through it. You don't want to do this because this requires you to use a map where you'd have to frost the bottom of the glass, but not the top. Not at this point. All right, so anybody have any preferences? Red wine, white wine? Brianna said red. Anybody else? You don't have to like wine, Zachary. You're an artist. Red, blue, red. Blue wine. Actually, there is blue wine, Moesha. There is blueberry wine. It's not really as blue as you might think it would be, like, you know, Mountain Dew blue, but it is bluish. There are blue bottles. So, all right, red wine. All right, let's see. Well, let's go with this one. That's a pretty nice shot. See if we can save it. Put it on a desktop. Yep, that will work. Actually, it looks like something's in the glass. So no, I don't like that one. It's like somebody stuck, I don't know, for one of a better description, weeds inside the glass. That may just be the reflection, but yeah, I don't know. Yeah, oof is right. All right, so let's do this. Nope, go back. There we go. That's not too bad. That one's not bad. Kind of looks like the same shot almost. Let's see. Yeah, actually, that looks like it'll work. Let's save that one. Now, a couple things about looking at glass. So we're looking also at the level of roughness. I'm not really seeing a lot of roughness. Most glass, especially for wine glasses, are fairly smooth. You know, the idea is you want to see the liquid inside. Wine is usually pretty clear. You know, it's not going to be hazy looking. It's not going to have a lot of roughness. You know, a lot of wine companies, they take pride in the clarity of their wine. You know, so there's no particulate matter in there. The cork doesn't interact. You know, that's just not considered good classic wine. Okay, so we got reference for that. And what kind of wine bottle shall we have? So let's find empty wine bottles. Okay, empty wine bottle outside. Here's a bunch of them. And actually, that's not bad. We can't do clear because it needs to be some color. So we got green, we kind of got a light amber, and we got a dark amber. See, that dark amber looks like a beer bottle. That lid is not a wine bottle. All right, here's another one. Looks like it's the same bottles, actually. Just a different shot. All right, so you know what? I don't think I've ever used this one. I know I've used the other one, but let's just go with that. All right, there we go. Let's open both of those up. And now we've got an option. We can pick our wine bottle color when we're ready. All right, so not too bad. Let me just make this a little smaller because my other monitor is definitely smaller. Okay, that looks like it'll work. We got this. And let's fire up Maya. Keep that just in case we need it. So we're going to do the exterior first. We got reference, we got a wine glass, we got wine in the glass, and we have an empty wine bottle or a bunch of them. We can decide what color we want later. All right, come on, come on, come on. We get RenderMan. There we go. We got Arnold. Good old Arnaldo. Okay, let's get RenderMan. Let's set our project. Zen Garden. Yep, that's it. And we did the daytime. Most of us did the daytime in the lighting, so let's do that. All right, I'm not seeing my background image, so that tells me when I copied my lighting from project 5 and made it project 6, it looks like it broke the link to my, yes, it did. All right, so not a big deal. Just select the dome light. Let's relink it. All right, so where are we? Ah, project 5, that's why. Let's go project 6. Zen Garden, source images, right there. Give it a couple seconds. Popped in. Let's do another render. Yes, that looks much better. Okay, good. And we're going to focus on the close-up. And don't forget that we hid the geometry for the long shot and we unhid it for the close-up. So channel box, layer editor, turn on your objects. And let's make sure Pixar surface on everything. Yep. There we go. Excellent. We're all set to go. Now, as I mentioned, the wine bottle has a label on it. That label we are going to throw onto a separate display layer and turn visibility off. So wine label. Turn visibility off, it's there. Now, when we go into project 7, we turn the label back on, we'll be able to play with it. But that label would only cover up our wine bottle. So we don't need that. Now I'm going to save as, since I got my scene prepped for surgery here. All right, lecture 7. Let's make clear glass first. All right, so clear glass, very smooth. First, select your geometry. This happens to be a NURB surface. So let's do that. And let's change our Pixar surface name, wine glass. All right, so let's get our little checklist up here. So, found reference. We assigned a new Pixar surface to the geometry. So now we need to turn off diffuse gain, skip primary specular, go to glass, turn up refraction gain, reflection gain to 1. Clear glass, which is what we have, is white by default. Excellent. Roughness, perfect. So diffuse gain, 0. Skip primary specular, which I'm going to do. Go down to glass, open up glass. Refraction gain goes to 1. Reflection gain goes to 1. Yep. Okay, refraction color is white. That is pure glass, clear glass. Roughness level, well, we'll see what we get. Refractive index, this is glass, perfect. Let's see what we get. All right, I'm going to turn off my talking head because now we're dealing with rendering and my video is probably going to get real jittery. There we go. All right, so what we're seeing here is the default level of roughness. If you notice, our reference isn't really that rough. That's, nice smooth surface. So if it's a really almost looks perfect, remember nothing is perfect, I will probably go and give that a 0.01. Just to throw a little bit of roughness in there. Now, I don't need to render the entire scene, so I'm actually going to crop out the bottle and the glass. I want to crop a little bit so I can see the shadow for when we start dealing with the bottle, but I'm just going to focus in on the glass.
How do you crop out certain sections of the render?
Just like we did in Project 1. Remember, we were doing small bits and pieces. You use the crop render, marquee it, and then you hit the render again. You have to render initially first using IPR.
And then you use that button up there, and then you just select.
This button's the crop button that lets you marquee, select the area, and then you hit R, which basically in the it window will render again, but it's only going to render that region.
Okay.
So we're not using anything new that we haven't done in the past. All right, so we got clear glass. We can see through it. We can see we've got a piece of clay inside the glass. Our glass is transparent shadow here, but the clay obviously is opaque because it's the default diffuse. All right, so not bad. At this point, let's save our scene. Why? Because we did a bunch of stuff to it. So right now, we are in pretty good shape. So let's do the wine inside the glass. All right, so basically, I'm just going to come here. There's my geometry. I can also go to wireframe. And I could have gone in here and selected the wine geometry in there manually. So I'm going to assign a brand new Pixar surface to that. Let's select that wine again. And let's go red wine. Okay, so we've got reference. We assigned a new Pixar surface to it. Let's do our normal thing. Turn off diffuse gain. Diffuse gain 0. Primary specular, we're bypassing completely. Refraction index, or I'm sorry, refraction gain up to 1, reflection gain up to 1. We've now made clear glass. Okay, the color is going to be based on our reference. Now, we're going to use that little trick that we did in last lecture where we sampled the reference image for color. So to do that, I've got my reference on my desktop. I'm going to double click in my color swatch. No, double click. No, double click. No, double click. There we go. My tablet pen is getting funky on me. All right, so here we go. Red wine Pixar surface. This brings up the free floating advanced color palette. Color wheel, under image, we're going to load. I'm going to go to my desktop, empty glass bottle, screenshot. No, I don't want that. That's what I want. I click open. So now I can click and kind of drag around. Remember, you want to avoid really super light areas. You also want to avoid super dark, shadowy areas. We're kind of looking for a neutral. Well, that kind of looks like maybe that's where the red wine is in there. Now, notice the value is pretty low. We may need to change that based on what we get in our render, because our goal is to get wine in our render that looks like our reference. It's got some clarity, but where there's dark shadowy areas, trees, foliage, that's going to be darker. Now, last, we need to find the index of refraction for red wine. And this is where the interwebs come in handy. So let's do a search here. Refractive index wine. Oh, chemistry of wine. Let's see what that does. That sounds fun. Awesome facts. No. No, we just want the refraction. Here we go. Okay, nice. Nice. That doesn't tell me anything. Alcohol content hydrometer. That's great. Beautiful. Love it. Where's my refraction index? I don't care about gravity. Acid, data. I don't see one final comments. Okay, so that was not fun. All right, let's try this one. Okay, American Journal of Enology and Viticulture. Okay, sounds impressive. So where do we go? Refractive index, wine, but it doesn't tell me what kind. Is it white? Is it red? They all look like they're 1.34. It looks like 44, 43, 45, 4.3, 4.5. So I asked for red wine, and how do we find out? No, I want that. Here's the article. No. Refractive index. What's that going to do for me? No. That hurts us. It burns our eyes. It burns the precious. Yeah, 1.39, but I'd rather actually have those numbers in front of me. Abstract. I don't want the abstract. Give me figures and data. Ah, the article said those were all red wines. Ah, very good. Thank you for actually looking at that, Brianna. All right, so, red wines. Yes, you are correct. Excellent. Thank you. So let's pick one. 1.344, 1.345, 346. Well, looks like 344 seems to be the, there's 1.343. 344 usually looks like it's probably the most common. So let's go with that. All right, so down here, 1.344. A little bit higher than water. So we found the index of refraction, and we're not doing glass panes. So let's do a quick IPR and see what we get. All right, so not bad. We're getting a little bit of blackness back here. So let's see now. Let's do a little analysis of our image. So the wine glass itself has 4 surfaces. With the wine in the glass, how many surfaces did we say it was? So we said 6, right? How about our wine bottle? How many surfaces? It's empty. There's nothing fancy about it. There's no overlapping fluted edge or mushroomed edge on it. So this is going to be the same, yeah, as the regular glass. So we've got 4 for the bottle, 6 for the glass. That equals what? How many surfaces where we have overlap right here? Well, actually, more so down here. How many surfaces for our ray to go through? Anybody? 4 for the bottle, 6 for the wine glass, total of 10, right? So we need to check our render settings. Remember, one of the last steps in the checklist, adjust the render settings, RenderMan, sampling, default ray depths. We have to adjust the max specular depth. Max specular depth, don't be fooled by the name specular. Okay, render man. Oh, I got max 2 on there. Wow, that'll increase my render time. Let's knock that down. All right, so all the rest are default. That's pretty good. So here, this is where we need to increase to 10. Remember, it's going to be the number of refraction and the number of reflection rays. Fortunately, RenderMan doesn't share them. Each aspect gets whatever number you put in here. So 10 automatically means 10 refraction and 10 reflection. So now with that number cranked up, let's do a quick render here and see if we get any better results. So now notice that kind of black hole is gone and we get a lot more sparkle to the glass. Does that make sense? So this is before we adjusted the default ray depths. This is after. Again, that's why it is in that checklist. So now we go on and let's go make glass for the bottle. Select the geometry. We've already got reference. Select the geometry, create a new Pixar surface for it. So wine bottle. Never thought increasing the max would increase the glass quality. Well, remember when we increase that max specular here, right? It's reflections and refractions. So not only were we missing being able to see through the glass all the way, but we're missing all that light bouncing around, bouncing through the surfaces. And that's really a big deal. You know, you got light bouncing around inside the wine itself. Plus now we've got enough, you know, remember this is self-reflecting, the wine glass. So here, after 4, it stopped. Now it's got 10, it can keep bouncing around. So basically, you know, we get rid of those super dark edges where just it stopped reflecting. And now we can see through everything. So yeah, it is a little bit eye-opening, Seth, when you first do it. But we're just trying to break it down, you know, logically and scientifically to kind of show you how this stuff works and why we need to do what we do. You know, it's kind of causality, if you will. We do one thing and it affects a couple of things, not necessarily just one aspect. Okay, so got our geometry selected, new Pixar surface. Turn off the diffuse gain. Can do. Bypass primary specular, easy. Let's make glass. Refraction gain, reflection gain, both up. Okay, now the color. We're going to do the same thing we did with the wine. Let's double click and load in our new reference. There's my bottles. And which one should we do? We've kind of got this, you know, lightish green bottle, kind of got this ambery bottle here. We've got, well, this one looks darker, but that's because it's behind a dark bottle. All right, so Moesha said green. Anybody else got a vote? No clear because it needs to have color in it. Brianna said amber. So we got 2 ambers, 1 green. Purple, I don't see purple there in our reference. Edwin said green. So we got 2 green, 2 amber. Zach, you got to revote. So we got 3 green. Zach says amber. No way. We have actually got a tie. So we got 1, 2, 3, 1, 2, 3. We got 3 ambers and 3 green. We need a tiebreaker vote. Edner, that's up to you. Seth said he can switch to amber. Okay. Ouch. Uh-oh. Looks like there's going to be glass color wars. Rock, paper, scissors. All right, so let's go with amber. All right, so here's our kind of greenish amber bottle. We even have a dark one back here. It almost looks purpley, but really is kind of green. Got an amber bottle back here. It's almost greenish as well. So let's try that. Notice how dark the value is and how high the saturation is. That value may wind up being way too dark for our scene, but let's see what we get. Let's finish our checklist here. What do we got? Okay, we're not doing thin walled. We've already adjusted that. The roughness level, well, you know what? The roughness level for glass, this bottle, let's go see. What does our reference look like? They look pretty smooth and hard. So, you know what? Our wine, I didn't turn down the roughness. So let me turn the roughness down to match the glass itself. For the bottle, let's see. The bottle. Well, let's make that just slightly rougher, like 02. Let's see what we get. So that wine actually has some roughness in it. So you can see it's a lot clearer now, and that bottle is super dark. Now, this is where, you need to adjust the value, because if your value is too dark, the bottle is going to be more opaque. So I like to bring my value up to at least like 0.6, 0.7. How does that look with my reference? Not bad. Actually, probably could be a little bit brighter. Let's go 7. That also looks like it's a little more green than it is kind of reddy brown. So I don't know. Let's do that. Yeah, that's a little much. Now I could always go back in, sample it again. Yeah, it's not bad. Kind of looking at this one, kind of comparing. All right, so maybe this one, maybe I just make it a little bit darker. Maybe a little less saturation. So just trying to eyeball it now. All right, so I can see through the bottle. I got transparent shadow here. And let's render out the whole scene. All right, anybody have any questions over anything we did? Does the workflow make sense? Pete's got no questions. Moesha's good. Seth got a lot to catch up on. Zach, no questions. Brianna, no questions. Edwin, no questions. Edner, questions? Not yet. Okay, good. All right, so this will give you an idea of the workflow. What we're going to do is take a break now. Cancel. I don't want to save that now. Let's save this. Time for a break. And then when we come back, we'll do the interior. I'll show you how to do the windows with thin wall. We'll do a couple of glass objects, and then you guys can work until the end of lecture time. And we'll go to lunch depending on how much time we spend working. All right, there we go. Let's quit out of here. So let's come back. At, let's go 11:07. So I'm going to stop the recording.